down arrow, choose submissions. I don't have any submissions, so I can't click on them, but y'all can. And the silly thing does not let me take the quiz. I wish it did. That way I could preview it accurately and record my score. But I can preview it like this. All right, more than one of these are true. I'm going to kind of look for the false statements. Arrays are declared using, yeah, of course that's true. If you declare an array of ints, you can also put strings in them. No, that's not true. An array is a variable that can store multiple values of the same type. Several people didn't select that one. Maybe I didn't word it like that, but the book does and the PowerPoint did. That's their definition of an array. An array is a variable that can store multiple values of the same type. I would have called it a list of contiguous data. But that is correct. I'm sorry if that threw you off. Everybody can take it again, though. Values of an array are stored in adjacent memory locations. That's very true. That's why they're the fastest data structure. Just rip through them by incrementing a memory pointer. And since they're all close together, then that memory can be cached locally in your chip. You know, your chip has different caches in it. You know, there's really fast memory that's next to your chip, and then there's, you know, slower memory. If the data can be put in that fast memory, then it can process incredibly quickly. So an array is a good way to do that because it's just a block of contiguous data. Once you allocate an array, its size will grow and shrink. That is not true. There are other data types that do that. An array is not. I believe the PowerPoint goes over one called a vector, which does. All right, write a line of code that will declare an array of type int. Should be named test. Should be 5 elements long. Now everybody knows how to do this, but some of y'all I counted wrong anyways because of this line. Don't use an initialization list. Here, I'll show you one correct answer that I graded wrong. That is correct. But I said don't use an initialization list. Why? Because I wanted to see you do this. That's correct. So if you use some permutation with an initialization list, just take it again and leave the initialization list off. This one, absolutely everybody got correct, I think. How to do a string full of colors. String colors is equal to this stuff. I'm just going to copy and paste it. So you Python users have already gotten the idea that arrays and lists are extraordinarily similar. However, in Python, lists will grow and shrink as you add and remove data from them, and arrays do not. A lot of people miss this one. This is actually a valid way of initializing every element in the scores array to 0. And why would you want to do that? Because otherwise, if you leave this part of it off, and it's declared as a local variable, not a global one, then it allocates space for the array, but whatever data was already in that memory location is what's in the array. So it's essentially garbage data. So if you do this, it wipes it all out. It sets every element to 0. So that is actually true. Which of the following statements will print the first element of the array? Everybody knows how to print the first element. It's element number 0. Which of the following will print the last element of the array? Well, since it's 10, you can go from 0 to n minus 1, where n is the length. So 9 is correct. Which is a good way? Well, you take the size of the array and divide it by the size of the data type. And there's only one of those that meets that. You know, they're all topsy-turvy. Some of them put the size of the int first divided by whatever, you know. Size of the array divided by the size of the int. I think the vast majority of people got that right. This one, I don't think anybody got them all right. I could be wrong. No, I think we had at least one perfect grade, so somebody got it right. There's one of these that everybody chose because it was correct. Let me find it. That one. This is correct. For int I is equal to 0, blah, 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 C out, IA, index I. That is correct. But some of y'all chose D as well. What is D going to do? Is it going to print the array out? Look what it's printing. What is I? It's just a counter, so all it's going to do is print 0, 1, 2, 3, 4. It's not printing the array, so D is an incorrect answer. There is a for each, or as they call it, a range-based array printing. That one looks kind of range-based, that one looks kind of range-based, that one looks kind of range-based. We just have to pick out the right one. For every X in IA, print out X. That one's looking plausible, but I'm going to look at the others to see what's wrong with them. For every X in IA, print out the element sub X. What's wrong with this one? X is actually values contained in the array. What if the first element of the array was 10,000? What if that was its value? Then we tried to print out, come on, IA sub 10,000. That'd definitely be an error. So this is definitely wrong. If you're using a range-based loop, you just print out that variable. You don't mess with the array variable as well. So that's definitely absolutely wrong. Let's go find the last range-based one. That would just try to print out the entire array all in one fell swoop. We're just printing the array variable rather than the X. So in this case, the correct one is C and an A. And I don't know if they're randomized differently for y'all or not, but hopefully you can spot them. Just look for the correct for loop and the correct for each loop, the correct ranged loop. Which of the following are true about parallel arrays? They are two or more arrays that contain related data. They may be of different types. Yeah, like you may have an array full of days, Monday, Tuesday, Wednesday, and and an array full of rainfall numbers. To use parallel arrays, elements of the same subscript are related. That's true. Well, it said 3 are true. We're pretty much guaranteed that if these 3 are true, this one's false. But let's look at it. Parallel arrays should be of different lengths. No. Same length. Which of the statements are true about partially filled arrays? Partially filled arrays are when the beginning of the array has been filled with good data, but not necessarily the whole thing. So, we do want to make the array large enough to hold the largest expected number of elements, but you don't want to be ridiculous about it. If you think that they may have, up to 10 test scores, you don't need to allocate room for 10 million test scores. Use a counter variable to keep track of the number of elements in the array. Yep, that's true. When you process the array, you should always go from beginning to end, ignoring the counter variable. No, you only go up to the counter. If you know that there are 10 elements in that array that are valid, you should only print out the first 10 elements. You shouldn't keep going. And by the way, if it looks like to you that you checked the right ones and it wasn't graded right, let me know so that I can go, whoops. Seriously, like right now, you don't even have to just flag me down if any of these are graded incorrectly. Which of the following are true? We're talking about two-dimensional arrays here. A two-dimensional array is like a matrix. So if you have 10 rows of 10 columns, you have 100 cells. So if it's 4 by 3, it will have 12 elements. That's correct. A nested loop is in fact the best way, so that's not correct. If it's got 4 by 3, it doesn't have 7 elements, so that's incorrect. To compare arrays, you must compare the arrays element by element. And that is true, unless you can come up with a way that I don't know about. And yeah, you might be able to call a method that somebody else has written to compare the arrays, but you're still comparing them element by element. It's like having 2 lists of names. I want to see if the names of the people taking this class are the same as the names of the people taking my Java class. What do I got to do? I got to put both lists in front of me and go down item by item and see if they match. And if there's a difference, then I know they don't match. So you have to compare them element by element. And a loop is the best way to do that. Only way to do that I know of. All right, and this is an example of a range-based for loop. Yeah, that's true. That's what the book calls it. Colloquially, I call it a for each loop because other textbooks call it that, and some textbooks, some languages even have the word each as part of the syntax. C#, for example, puts for-each, and then puts this syntax there. Kind of neat to have an extra word for it, but C++ and Java chose not to do that. Okay, so y'all can take it again if you want. Kind of would rather you not do it at this point in time, unless you already have. I can't stop you. All right, we've obviously lectured enough about arrays to have a quiz on it. It's time to move on to the next chapter. We started chapter 8, searching arrays, and really there's not much to talk about there. I don't really feel that we need to write a lot of code about searching and sorting arrays, but we'll do it at least the searching the array. And I've already talked about a linear search versus a binary search. That is correct? Okay. The book talks about the source code for doing a binary search, and I'm going to skip that. You have the concept in your head, and you could look up how to do it if you had to do it. Then the code is already out there. You don't have to do it yourself. That's the wrong language. Okay. So a linear search is when you start at the beginning of the array and you keep looking until you find it. And I know we've written one of these before, but we're going to write it again. And that'll be the last time we do this. Previously, we may have called it an index of algorithm, and we may have written it with respect to strings. I don't recall if I had this class do that, but we will do it with arrays right now. New project, get our boilerplate going. Oh, I forgot to stop. Any questions over the quiz? Or did it all make sense? Y'all all take it again, get 100 on it? Please do. Right-click source files, add new item. It's a C++ file. Paste it. There we go. Okay, let's declare an array, I don't know, of colors. String colors is equal to, and just make a list of like 5 colors. Doesn't have to be my colors. I always go RGB, red, green, and blue, and then tack a few more on. Now say we wanted to replace one of those colors with another one. The user has specified that orange is supposed to be removed from the color list and replaced with, I don't know, brown. Well, we have to find the index value of that one in order to do it programmatically. Yeah, we could just edit the source code, but just bear with the example. For funsies, let's print the list out as it is to begin with. For every string in the colors list, see out that string. But now we need to find that element. I'm going to declare an integer, which is going to represent the index number. When we're done, the index number will either equal the index number of the one we're searching for, or it will equal -1 to indicate that it wasn't found. Now let's use a for loop. For int I is going to be my index counter. Started at 0, and we need to go out to the length. Well, I really should have declared the length beforehand. I could use size of right in the middle of the for loop, but it starts to look nasty. So above that for loop, I'm going to declare a constant that's the length of the colors. So constant int length is equal to size of, and you can guess how this works, colors divided by the size of a string. Now my for loop can look better. For I is equal to 0, I is less than the length, I plus plus. But I'm going to tack on an extra clause here. I think when I wrote this last time, I just used a break statement to bail out. This time I'm going to use an and. As long as we haven't found it yet, as long as found at still equals -1, we want to keep looping. So add that to your condition of your for loop. Once we find it, we're going to set found at equal to something else, some value between 0 and 4, and so that'll cause it to exit that loop. Let's compare. Well, we need a target to search for. So above int found at, let's ask the user to enter color. How about replace what color? And we'll let them type in a color into a string called target. What did I do there? That's horrible. String target cn into target. Okay, so these are the 3 lines of code I just added above my for loop. What goes in our for loop? Just an if statement. Find out if our element, if colors at position I is equal to our target, then great, we found it. Set found at equal to I. And since we put that in our for loop right there, that means that it'll stop the processing of the loop at that point. So really this is going to find the first occurrence of it. Like if this thing had red as every element and we said search for red, it's only going to find the first one. And that's okay. If we get here and found that is still equal to -1, it means we went through the entire array without finding it. So we're going to check for that condition. If found at equals -1, we're going to print out an error message. Cout could not find color, and then let's print out the color that they entered, the target, and do ENDL. Else, let's change that color. Colors found at is equal to brown. Then let's print out our list again. For every string S in the colors array, cout I need to check something up here. Yeah, cout ENDL. All right, I may have gone fast. I'll try to get as much of the code on as possible. Here's the end of it. Does anybody need to see higher than this? Anybody getting compilation errors? Run it, see what it does. Run it 2 times. The first time, type in a color that does exist. And then the second time, type in a color that doesn't. Well, look at all the nasty stuff. Why did it do that? Oh, colors. I made a mistake. Can anybody else spot the mistake? There's a mistake in this for loop. If you scroll up and compare it to the other for loop we wrote, what's wrong with it? Yeah, why am I trying to print out the entire array? It's just that looks ghastly. Change that to an S because that's our variable right there. Did it change it? Did any of them become brown? Oh, not equal. Can I type equal? No.
Oh.
There you go. Okay. Okay, cool. Run it twice, watch it produce an error. Oh, I see. You're right. Okay, I didn't spot that. Alrighty, that's a linear search. Starts at the beginning, runs to the end. If the data was sorted, great. We wouldn't have to do a linear search. We could do a binary search on it, which, as we discussed, for large data sets is far more efficient. You ready for me to tab away? You got it now? Introduction to sorting algorithms. Say we wanted to sort that data. There are 2 kinds of sorts, and I really don't feel like making us write the sorts, but I would like for us to know the sorts. I'm wondering if all right. Apparently, let's see if this is a good video or not. Wonder if y'all can hear it.
Selection sort is a special type of sorting method in which each element of an array is scanned to find the next smallest
That's
value.
not really loud enough.
Then, the smallest value of the array is placed at the front. Next, the array is scanned again for the next largest element. The next largest element is then placed in the next spot.
I want to get to it where it actually demos it. If it doesn't, here we go.
Longer stretch. Selection.
So what's going to happen is that we're going to run through this array, find the smallest value, and swap it with the first one. So we're going to go,
Keeps going until they're all.
right, exactly. It's going to go, is 5 smaller than 8? Yeah, sure is. So it puts the 5 there. It keeps going there, but now there's a 5 there. Is 7 smaller than 5? Nope, so it leaves that one alone. Is 1 smaller than 5? It sure is, so then it swaps those two. And we'll see if her hands do that.
Array sort is an array of 6 int values that are placed in a randomized order, a call to the selection sort method of iterations. Notice how 2 elements are swapped to place the smallest value in its correct positions.
Like that.
Some of the later elements are taken out of order to place the values in ascending order. Some of how to, a call to the
So,
selection sort.
the selection sort, that's what it does. Starting here, it searches the entire array for the smallest one, and then it swaps those. Now you know this one's right, so we don't start here anymore. We start here. It searches the entire array, what's left of it, for the next smallest value, puts that one there, which in that case would be 3, and then swaps those two. Now we know that these two are correct, so it starts here. And it goes from here to here, finding the smallest one of the remaining, and it swaps those two. Then it does it for these 3, finds the smallest one, puts it there. Then it does it for these 2, puts the smallest one there, and then we're done. Then there's something called a bubble sort. The way the bubble sort works is I actually started to describe that, sorry, is it compares the first 2 and then goes, oh, which one's the smaller? Put that one there. Then it compares the next 2. Or actually, it does the largest. Which one is the larger of the 2? And it puts the 8 there. Which one is the larger of these 2? Well, 8 winds up there. Which is the larger of these 2? Well, the 8 continues to march up. Then it goes, which is the larger of these 2? 8 or 9? Well, no, it's 9. So we can't swap them. And then it goes here and it searches, which is the larger of these 2? 9 or 3? It puts the 9 there. So it bubbled the largest one all the way to the top. Now that we know that the top one is done, we repeat that process, but stop there. Look, is it, like that. So that's the difference between a bubble sort and a selection sort. And sorting is something that you could go to school and write a PhD paper on. It's really important because data sets are so large nowadays. If you think about how much data Google has to index in order, for their searches to work. How do their searches work so insanely fast? Well, they've already got the data sorted and indexed in ways that are easy to access. But the sorting of it, bubble sort and selection sort are not very efficient sorts. They're easy to write, but they're not very efficient. They're not the fastest ways. There are much faster ways. But they are easy to write, so that's why beginning programming textbooks talk about them.
What's the fastest way?
One of them is called quick sort.
Sounds quick.
Yeah, sounds quick, huh?
What's it look like?
Let's see if we can find an example of a quick sort.
There's a kid in my engineering class that's interning at Google this summer.
Oh, yeah?
Yeah, he's from Berkeley.
Oh, cool.
Lucky.
Well, we have some blocks here moving around. Let's see if we can watch.
Sorting this array of integers from smallest to largest. Here we have the integers 6, 5, 1, 3, 8, 4, 7, 9, and 2. First, we pick the final element of this array, in this case 2, and call that the pivot. Next, we start to look at 2 things. 1, the lowest index, to which I'll refer to as sitting to the right of the wall, and 2, the leftmost element, which I'll call the current element. What we're going to do is look at all the other elements other than the pivot, and put all the elements smaller than the pivot to the left of the wall, and all of those larger than the pivot to the right of the wall. Then finally, we'll drop the pivot right on that wall to put it between all the numbers smaller than it and all the numbers larger. So let's do that. Pick up the 2, put the wall at the beginning, and call the 6 the current element. So we want to look at our current element, the 6, and since it's larger than the 2, we leave it there to the right of the wall. Then we move on to look at the 5 as our current element, and see that this is again larger than the pivot, so we leave it where it is on the right side of the wall. We move on, our current element is now 1, and oh, this is different now. The current element is now smaller than the pivot, so we want to put it to the left of the wall. To do this, let's just switch the current element with the lowest index sitting just to the right of the wall. Now we move the wall up 1 index, so the 1 is on the left side of the wall now. Wait, I just mixed up the elements on the right side of the wall, didn't I? Don't worry, that's fine. The only thing we care about for now is that all these elements to the right of the wall are bigger than the pivot. No actual order is assumed yet. Now back to sorting. So we continue on looking at the rest of the elements, and in this case we see that there are no other elements less than the pivot. So we leave them all on the right side of the wall. Finally, we get to the current element and see that it is the pivot. Now that means that we have 2 sections of the array, the first being smaller than the pivot and on the left side of the wall, and the second being larger than the pivot to the right side of the wall. We want to put the pivot element between the 2, and then we'll know that the pivot is in its right final sorted place. So we switch the first element on the right side of the wall with the pivot, and we know the pivot's in its right position. We then repeat this process for the subarrays left and right of the pivot. Since the left subarray is only 1 element long, we know that's already sorted because how can you be out of order if you're only 1 element? For the right side of the subarray, we see that the pivot is 5, and the wall is just left of the 6. And the current element also starts out as the 6. So 6 is greater than 5, we leave it where it is on the right side of the wall. Now moving on, 3 is less than the 5, so we switch it with the first element just right of the wall. Now we move the wall up 1. Now moving on to the 8. 8 is greater than 5, and so we leave it. The 4 is less than the 5, so we switch it. And on, and on. Each time we repeat the process on the left and right sides of the array, we choose a pivot and do the comparisons and create another level of.
Now his data was chosen in such a way that it only took 2 passes and it wound up miraculously sorted. So it's not really that fast necessarily, but you know, one thing you can think is, wow, that's kind of hard, to remember. Or maybe he did such a good job of explaining it. I think that's actually about the best explanation I've ever seen. But that's one of the fastest ways. There are other fast ways that require you to allocate a copy of the array. So if you have 10,000 elements, you have to allocate, another 10,000, and you can then start, swapping into that other one in the correct place. So if you have plenty of random spare, then I think the insertion sort relies on that. That may be the first time I've played a video in one of these classes. I hope that was entertaining. So the bubble sort. You compare the first 2 elements. If they're out of order, you exchange them. Then you compare the second and the third and the fourth and the fifth, and so on. The highest value percolates all the way up to the top. Then you repeat that going from the beginning all the way to the end minus 1. And then you repeat that in the end minus 1. And you keep doing that until there are no swaps done. But if they were all perfectly sorted to begin with, you don't need to keep doing it. You would just run through it. You would find out that there were no swaps to be made, and you would stop at that point. Bubble sort trade-offs. It's easy to understand and implement. It's inefficient. It's slow for large arrays. The selection sort. You find the smallest element in the array. You search the entire array. You grab the smallest element and you put it in the spot 1. Then you search all the rest of the array. You find the next smallest element and you put it in spot 2. Actually, I should have said 0 and 1, huh? And you keep doing that until it's all in order. The benefit, it's more efficient than bubble sort. Not quite as easy to bubble sort to understand. Actually, I think it is, but all right, and we haven't talked about vectors yet. Kind of need to. I think we need to go back to chapter 7 and talk about vectors. Vectors in physics, you know, is a point that has, you know, a force applied to it, yeah. And it doesn't quite mean the same thing in this. What a vector is it's something that takes care of the fact that arrays can't grow or shrink. So it can hold values of any type. You Java programmers have seen this called an array list. It's one implementation of a vector. And it automatically adds more space as it's needed. So what you do is you use the word vector and then you put your data type in there. If it's a list of names, you put string. If it's a list of floating point numbers, you put float or double there. It automatically adds space as more is needed, so you don't need to put 12 or 1000 or whatever. You don't need to determine the size at the start. And you can still, in this language, unlike Java, use square brackets to access it just as easily as you can an array. So we have to include this keyword, # include vector. Let's add that to the top of our program. # include vector, V-E-C-T-O-R. Here's how we declare a vector to hold ints. If we wanted to create one with an initial size, you could. If you wanted to create one with an initial size and set all the elements to 0, you could. But let's just do this kind of thing. Except let's make it strings, since we were playing with colors. Go back here, vector of string, let's call it hues rather than color. If it was a vector of ints, no reason to type this, then we would do that, you know, for doubles, whatever. You can initialize a vector almost the same way as we did it with an array. With an array, we had to use the equal sign there. With a vector, we do not. To add an element to the array, you use this weird word, push back. So let's push back some elements of the array. So hues dot, other languages call it add, which I like much better than the word pushback. Push underscore back, and we're going to add the color pink to it. I'm just going to copy that entire line now because I don't feel like typing it again, and I'm going to add on a couple more colors until I have 5 of them. Pink, slate, onyx, all those wall paint colors, you know. Forest green. Somebody come up with a 5th color. My brain broke. Silver. There we go. Now we have 5 colors in our vector. We could use a range-based for to print them out, just like we did here. For every string S in our hues list, see out that string. And then I'm going to see out just a line to separate our input, you know, so that we know that we're getting to a different part of the program. Now when we run it, it's going to print these hues before it starts doing the rest of our program, whatever we had to do earlier. There we go. So it printed them in order: pink, slate, onyx, forest green, silver. Replace what color? I don't feel like playing that game anymore, so I'm just going to type something in. There we go. There's a whole bunch of sort of methods that you can call on it. There's one called pop. Now that I've added a pop to it, that's going to remove the last element. So it's only going to say pink, slate, honest, and forest green. Watch me be wrong and watch it take pink off, but it shouldn't. There we go. Pink, slate, onyx, forest green. It left silver off. If we actually wanted to do something with that word, string, whatever, I can't think of a name, removed color, popped color, string spop is equal to that. And I've done that, I've gotten the syntax wrong, so I'm going to just undo that. The idea, this is an implementation, among other things, of something known as a stack. A stack is a LIFO, last in, first out structure, like a stack of plates. The last plate you stick on the stack is the first thing you take off. So if I have, you know, a stack of pages, I push that onto the stack. I push this one on the stack. I push this one on the stack. Now I need a sheet of paper. I pop that one off the stack. Then I push something else onto the stack. Then I go, nope, pop it off. Pop it off again. The very first one I push is the very last one I pop, and then the stack is empty. And that's opposed to a queue. A queue is something where it's first in, first out. You'd be really annoyed if you tried to send something to the printer and then the last person who printed got to jump in line and their job came out first. You want it to be a queue. First in, first out. FIFO. Put something down again, put something down again. Oh, somebody needs a sheet of paper? Pull it off the bottom. Put something down. Whoops, somebody else needs it. Take one off the bottom. Put the last item down. Keep pulling items off. Keep pulling from the bottom. This is the last one that I put down. It's also the last one I pull off. So queues are first in, first out, while stacks are last in, first out. And this nomenclature, this push back and pop back, are stack terms. You can get the size of the list if you need to count it with the size operator. C out, you know, list or vector size hues dot size. Since we popped something off of it, it should only be 4. Vector size 4. So why are vectors cool? Because you don't have to allocate a maximum size. You're making a grading program and you don't know whether there's going to be one class in this, one student in the class, or whether there's going to be 1,000 students in that class. With an array, you'd have to allocate 1,000 slots. A vector, you just create it once and then it grows as you need it to. Removing elements. You can use pop back to take off the last one. You can wipe out the entire list with dot clear. You can check to see if the list is empty with dot scores. Let's write a little while loop that will empty out the list. So I'm going to go back over here. We already have this for loop, which prints them out in order from beginning to end. But now we're going to do another one. While Hughes dot empty is equal to false. And there's other ways I could word that. I could just put the not there, you know, like that. I kind of like seeing the word equals false, honestly. While it's equal to false, I really need to remember how to use dot pop back. Is there no way to retrieve the data as I do this? Nope, that doesn't do it. Excuse me for engaging in a little bit of Google. Why doesn't popback have a return value? I have Googled regarding this and found out that it makes it more efficient. Is that the only reason for making it so retarded? I mean, making it so in the standard. Okay. And so how would we get the last element out, since I can't do that? We could use the size of it. But remember, if you have an array of size n, what is the last element you can get a hold of? N minus 1. So let's do that. Int n is equal to the size of the Hue array. Let's get our string out. Hues at position n minus 1. And then we pop, and then we can print our string out. Let's make the words a little bit more interesting now. Popped. I'm sorry. The word that I used there just a moment ago is disparaging, and I shouldn't have used it. Okay, there we go. Popped. Like that. We will see that this does it in the opposite order of this, because this is this just rips through it in the order in which they're stored, whereas popping takes things off the end. And so we pop something off the end, we print it out, and we keep popping until Hues really is empty. And there we go. We popped green, we popped forest green, we popped onyx, we popped slate, and we popped pink. The opposite order. So this is how we pulled the value back out. Or you use a for each loop. Either way is a good way to get values out of it. This is like the most efficient one to write. It's a great way of doing it. If you have an index number, you can pull it out like that. You just put the index value between the square braces just like you do with an array. Anybody need to see this? Anybody still typing? Okay. I did not mean to close that. Why did it close? Probably because we were just about at the end. Removing vector elements. Here's how you check to see if it's not empty. I used scores.empty. I used hue.empty equals false. You can also just do that while not scores empty, taking advantage of the exclamation mark. Other useful member functions. At. Return the value of the element at position ELT. Why is that necessary when you can just use the square nomenclature? I don't know. Capacity. Returns the maximum number of elements that can be stored in it without allocating more memory. I'm kind of curious about that. I'm going to come down here and where it says vector size, I'm also going to print out the capacity of the vector. So I'm just going to copy that line, paste it, and make it say vector capacity. And then instead of printing out hues.size, I'm going to print out hues.capacity. Am I getting an error? Why, yes I am. I forgot to put parentheses after it. Hues.capacity with parentheses. And there we go. It says it has a capacity of 6. That means that some reallocation will occur to give it some extra space once we add more than 6 elements. And it'd be interesting to watch that capacity grow as we added elements, but I think that's almost knowing too much about it. The idea of a vector is that you don't have to care how much space it's occupying. You just keep putting stuff on it and it'll manage it all behind the scenes. Reverse. You can reverse the order of the elements in the array. Swap. If you want to exchange the contents of 2 vectors, you could do that. If we had a vector called colors and a vector called hues, and we wanted them to swap, we could do that in one fell swoop. All right. We have talked about vectors. We have talked about arrays. We have finished 8 pretty much. If we go back to 8, we'll see that the last topic in it, 8's the shortest chapter in the book, is how to sort and search vectors. And all it says is that they can be applied to vectors as well as arrays. You have to modify your functions a little bit. You can pass arrays in as arguments to a function. You can also pass vectors in. But we could declare a function, void print them, that takes an array of strings. I'm just going to call it SA for string array. And it's going to use a for each loop to print them out. For every string S in the S array, cout. Let's make this look real pretty with an asterisk in front of it for some reason. Followed by S, followed by ENDL. I'm getting an error.
You swap the brackets and the essay.
I'm not seeing what's wrong yet. Yeah, I could do that. Oh, yeah. Excuse me, I was doing Java there for a minute. All right. It's not liking the fact that I passed in an array into a method. Typically what you have to do in this kind of case is actually use an index-based counter. So we're going to rewrite this to use an index-based counter, and it's probably still not going to work. But let's give it a shot. Well, we need a counter. Int I is equal to 0. Let's get the length of the array. Int length is equal to the size of the array divided by the size of a string. Now we can write our for loop. If I'd written a for loop, I could have gotten rid of this int I. I'm going to delete that. for int I is equal to 0, I is less than length, I plus plus, cout a star followed by the array at position I. Hey, this one may work. It's not giving me any grief. Well, I didn't call print them on any data. So down here I'm going to make a new array, string names, string, not strings, names is equal to Bob, Joe, and Sam. And then just print them names. So when I run it, I was expecting it to print out Bob, Joe, and Sam. It did not seem to do that. I'm going to put a print statement right here to make sure that it actually went into the print them method. I forgot my semicolon. It went into print them, but apparently the length is 0. So the problem is that when you pass in an array as a parameter, C++ loses track of how large the array is. It no longer really knows. So we need to pass in a length as well. So instead of calculating the length, we're just going to pass that in. That means that I can delete this line, int length is equal to, but when I print the names, I better specify how many I want to print. And yes, I should actually calculate this rather than just hard code 3, but this is just to demonstrate. Then it prints them, Bob, Joe, and Sam. So the takeaway here is that it's absolutely great to write methods that accept arrays, but you lose the ability to calculate the length of the array, as far as I know. If it were a vector, you wouldn't lose that ability. If we made a version of printem that accepted a vector, no problem. We wouldn't have to monkey with passing a length in at all. What could we do if we didn't want to even have to pass that array in? How could we make this names data available to this printem function without passing it in?
Make it global.
I could make it, yeah, a global variable. I could have defined an array up here and then just written this one to use that array. Now that wouldn't be very flexible because then it would be hard coded, well, it would be coded to only use one array, which isn't great. When you have passed in an array, you can monkey with its data too. Let's make this silly thing replace everything that it prints out with the word ha ha. We are changing the element after we print it out. We print out the word Bob and then we change that element to ha ha. Go down to where you create the array of colors and then call print them on the colors. Scroll down here. Right here, we created a list of colors. Colors is equal to red, green, blue, orange, black. And now we do print them. Print them. Colors, and it's 5. We really ought to be calculating the size. Now when I run it, it's going to print out our three names? It didn't even seem to. It only printed out one name.
Figured out mine.
It worked on yours?
Yeah.
I wonder what I've done to break it. But you notice down here that it printed them, but then the next time we printed them with a for loop, all the data was destroyed. And that's not the real point of doing that, but the point was that your method, how odd. Yours worked. Did it work for everybody else? Did it still print out Bob, Joe, and Sam? But it did for you? I gotta see. Crazy. Captain, I cannot break the laws of physics. Why did that happen? Mine is only printing the first one of the list.
Yeah, mine printed them. I had to scroll up.
Is that what's happening? I'm just not scrolling up. Okay. All right. So, we demonstrated that we could change values. I think that's enough to say about that. You could write a function that would swap two elements of an array, like this. Void swap. You take your array, and then you pass in an x and a y. And to swap two values, you need a temporary. You can't just say this one is equal to that one, because then you lose the other one. So let's allocate a temporary string and set it equal to the x position. And then we will say the x position is equal to the y position. And then we will say that the y position is equal to that temporary value. You see what's going on there? If I pass in a 1 and a 3, x is equal to 1 and y is equal to 3, we're going to say, oh, my temporary value is the one at position 1. Then I'm going to say replace position 1 with the one that's at position 3. And then I say replace position 3 with whatever was stored at the temp. So before our call to print them, do swap, and let's swap the names Bob and Sam. Bob is at what position? 0. And Sam is at which position? 2. Okay. So now when it prints them out, it ought to say Sam, Joe, Bob, rather than Bob, Joe, Sam. Sam, Joe, Bob. All right, I think we've done enough for today. Especially since it's 40 after, getting there.